Hey guys, this is Siri, and today we're going to, sort of dive into limits. We're not going to do the rigorous definition of a limit just yet, actually. In this video, we're going to be getting an intuition for limits, right? We sort of touched on limits in the last video. And on the last video, we were saying that, as a point gets closer and closer to the point of interest, we see a more accurate slope for the instantaneous speed, right? But we can have a limit for anything. The limit really just asks what happens to something when we get really close to something else. So in the previous video, we said what happens to the slope as we get really, really close to x equals 1.5 hours or t equals 1.5 hours. In this video, right, we can also do it to the function values themselves. We can find the limit of a function. We don't just need to find the limit to identify what the slope would be. What we can actually see what the function value would be as we get closer and closer to a particular point. And so that's what we're going to be doing in this video. We're going to get an intuition for that, and we're going to do it in the context of finding the limit of a function. Okay, so we're going to say that we're going to be finding, the limit of a function. Okay? The limit of a function. Okay, and so let's take a look at an example, right? This is going to be an intuitive understanding. We're not going to get into, the delta epsilon definition in this video. I promise we're going to get into that in the next video. And so right now, let's just take a look at an example to get an intuitive understanding. So f of x equals, let's say that it equals 9 minus x squared over 3 plus x. We've seen functions like this before, hopefully, right? Rational functions, where we have a polynomial in the numerator, a polynomial in the denominator, and we sort of see what that looks like. Okay, so just for information, as we're looking at limits, let's write down what the domain is, right? We can say that the domain of this function is what? What values can the x values take on? Well, we see a problem in the denominator just for one value, for -3. So the domain is a set of all numbers except for -3. Right? So the set of all real numbers except for what? For -3. Okay? And the reason is because we can't divide by 0. We can't. That doesn't work, right? 4 divided by 0. We can't do that. We can't divide by 0, which is why we have this special condition that we can't set x equal to -3 to get an output for this function. Okay? However, right, in the context of limits, right, we can get really close to x equals -3. We can. The points points like 2.999, I mean -2.999 or -3.111 or 001, right? Those exist, right? It's just -3 that we have a problem with. X equals -3 that we have a problem with, right? So, right, getting into this idea of a limit, we can evaluate the function at points like those, right, that we just discussed. And so let's take a look at some of these values. Let's create a table for ourselves. And let's have a table with x and f of x. Okay? So -3.1, let's take a look at what the function value is when x equals -3.1, -3.01, so we're getting really close, and then -3.01, 6.001. Okay, and we'll see that it's 6.1 here, it's 6.01 here, and it's 6.001 here. Okay, so just like we approach a particular x value, we see that the function also approaches a particular y value. Okay, this might not always be the case, right? And in those cases, the limit wouldn't really exist. But yeah, so we see the f function value getting really close to something, right? Getting really close to 6, right? But we've taken a look at, so if you see the number line, right? And we have 0, -1, -2, -3. -3 is here. So -3.1 or would be like here. But we didn't check out the other side. What about like -2.99, right? So to the right here and to the left, right? So that's what we call the left and the right limits, which we will also get into later. But you know, let's draw another table for ourselves, which takes in x values such as -2.9, -2.99, -2.999, right? So what do the y values look like here? Well, the y values look like 5.9, 5.99, 5.999. Okay, so we see sort of like something interesting, right? We approach 6 from this side, right? From the 6.1s and that side, but we also approach 6 from this side, from the other side, from the left side, from 5.9. And in some cases, this is not the case. Sometimes the left limit approaches something, and the right limit approaches something. So this is a really special function, right? The limit exists at this point. So the two tables show that as you approach x from either, x equals -3 from either side, right, we sort of get 6, right? So as x gets closer to -3, right? So let's sort of draw that. Can we draw that? And so let's look at it algebraically, right? Let's simplify this first. 9 minus x squared divided over 3 plus x, right? Can we rewrite 9 minus x squared? We can rewrite it like this. We see, you always have to be careful when you're canceling things out, but it's helpful when you are just trying to find the limit. And we'll see that even though the function value itself doesn't exist, we can see that the limit exists. So that's sort of the idea that I want to sort of highlight in this video, is that even though the function value doesn't exist, may not exist, the limit can. So even though it's very risky to, cancel things out like this, it's okay when we're dealing with limits. Okay? So we can cross out the 3 plus x, and so what do we get? We got 3 minus x. Okay? So that's the limit of the function at any point. Okay? So let's take a look at this function, right? 3 minus x, that's a line, right? Okay, okay, the domain is the set of all real numbers except for -3. So we have a line. It's going to look like that. Right, the x-intercept would be 3, the y-intercept would be 3. You think we want to make it, I'm going to extend it a little, right to -3. What's going on at -3? We have a removable discontinuity at 3. And that'll make more sense when we talk about continuity and we define that a little more rigorously. But I'm just going to throw that word out there. We have a removable discontinuity. We have a hole here. So like here, we have a hole. And so we see that as we get really, really close, we think, the function thinks that it's getting really close to a value 6, right? That's what it thinks, right? But it doesn't actually exist. But the limit does. The function value here is a hole. It doesn't exist, but the limit does. And so that's what it would look like visually. Okay? So we have a removable discontinuity. And let's put this in words. Even though we cannot say, let's put this in not words, I mean more math notation. We cannot say that f of x equals f of -3 equals 6. -3 equals 6. Can we say that? No, we cannot. We cannot say that. However, what we can say is that the limit as x approaches -3 is 6. Okay, so how do we write that? We write the limit, LIM, limit, and the notation is like this. As x as x approaches -3 of what? What are we talking about? We're talking about f of x, the function f of x. And what is that limit? That limit is 6. And so that's how we write it. Okay? Okay, cool. I think that that's it for this video. And as you can see here, even though that the statement here, cannot tell you what the actual function value is, we can say what it looks like around that point. Okay? And yeah, now I think that's it for this video. So we sort of got an intuitive understanding of what a limit of a function is, right? What does a function value look like? What do the function values look like at a particular input, for a particular input and output value pair? And so that's sort of like a simple example. We looked at it. We looked at tables. We looked at the function. We looked at it. We simplified it algebraically, and we graphed it. And we claimed that even though the function value may not exist, the limit can. Okay, and I think that's all you have to take away from this video. And in the next video, we will really get into the formal definition of a limit, and we will, deal with all those epsilons and deltas, and you can look forward to that for next time. Okay, thank you so much. I hope you learned something new, and I'll see you in my next video. Bye.